On camera.
All right, I guess we'll go ahead and get started. So today and next week, the topic of the seminar is going to move to the subject of energy and agriculture. And today, our speaker is Dr. Terry Walker. I'm sure a lot of you know Terry, particularly those in environmental engineering. Dr. Walker is a professor of biosystems engineering in the environmental engineering and earth sciences department. And he is involved with teaching and research. He teaches a number of different classes, including classes on bioprocess engineering and on green energy and biofuels. And his research is pretty varied, but I think one of the main focus areas is on biofuels from living biomass. And I know he's doing some work on biofuel crops and also utilizing microbes in biofuel production. So with that introduction, I'll turn it over to Terry. Thank you.
Thank you. Yeah. Thank you. So I tried to come up with this a title that had some enthusiasm in it, because I'm very enthusiastic about this whole subject area, particularly how it involves agriculture, but and energy primarily. But this, I was just telling Jeff and Kelly that this logo was actually designed by a graphic design student that participated on our biodiesel project. We have a creative inquiry project that's been going for about 10 years. And then we were lucky enough to build a facility and then also hire the person that helped build the facility, David Thornton. So some of you have worked with him. It started really at this point. We grew it out of a few students, graphics design, a biosystems engineer, and another person from mechanical engineering. So it's always been really kind of broad that way. So we kind of invite anyone that's interested in biofuels to participate in our creative inquiry classes that we offer every year. Just sort of a program overview of what I do. I work a lot in bioenergy, but also work in bioproducts. My dissertation at the University of Tennessee, and I was working with Oak Ridge National Lab, and one of the extraction gurus of the world. I got very lucky to work with him, Dr. Hank Cochran, who is the director of the chemical technology division there, started me into this whole bioproducts area. So I was started primarily with extracting oils from fungi. I was very interested in algae as well. So later on I got into the algae area, but we were primarily extracting either pharmaceutical type compounds or nutraceutical compounds that had very high value. So omega-3 fatty acids is an example. You see this a lot in supplements and that type of thing. That's my dissertation work. And over time, I knew that a lot of this oil could easily go into fuel, but there was really no funding for fuel at that point. In fact, they killed the funding in 1997. That was actually started under the Carter administration back in the 70s on algae oil to fuel. Oil was very cheap at that time. And of course, as over the next 10 years, we saw what happened to oil prices. They skyrocketed to over $150 a barrel. Suddenly, there was this new funding for algae research for biofuel, and I got heavily involved in at that point. So a lot of my work is there. We also worked on bioethanol production from sustainable sources. So a lot of people hear about corn not being very sustainable, which is not, because you're just taking starch and trying to convert it over to ethanol from just a small part of the plant. So the idea was to take all of the plant or part of the plant, the cellulosic part, and then convert that to biofuel, and that's going to be more sustainable. But even more sustainable than that would be, let me go back, is switchgrass. So we got our first grant working on switchgrass by converting this over to bioethanol. So that grant lasted till about 2013, and a lot of the equipment that we had came out of that grant along with USDA, so that you see here, like this bioreactor. I work a lot in the bioprocessing area. So this is actually a pharmaceutical grade bioreactor I have in my lab that we can go up to 20 liters and produce pharmaceuticals that come from sugars that would ultimately come from the sources that come from photosynthesis, primarily from plants or from algae. It really gives us the best, more sustainable footprint for producing chemicals, for producing foods, nutraceuticals, and energy. So all of these areas kind of combine together. We also produce enzymes. So lipases are an example where we're looking at using lipases to produce biodiesel. So we're trying to get away from really harsh chemical catalysts that are used today. And what we're using right now in our facility, we're using potassium hydroxide, which is a strong base. It eats up equipment. You have to have stainless steel. Even the stainless steel gets corroded by this stuff. So we would love to move away from that and go to a more biological or natural type system. And we use enzyme lipases. So at the moment we're working with Novozymes they're located, they have a plant in Franklinton, North Carolina. And we are using their lipases to experiment and try to make biodiesel that way, comparing with their enzymes. And then most recently, we have acquired a gasification reactor that's now down at Cherry Crossing. So both the biodiesel pilot plant that's shown here and this gasifier are located there. And the idea is to scale up and use biomass. This would be very good for forestry, so we can take the byproducts that are coming out of our Clemson forest. We have the second largest experimental forest in the nation. So that is an impressive facility that we can take advantage of by taking some of their byproducts, convert it over to energy, basically just converts any type of organic material will then convert at very high temperature, about 1,000 degrees Celsius, converts over to hydrogen and carbon monoxide, and both of those will then feed back into an engine. There's an engine behind here, and so this is what's called a combined heat and power unit. So it produces both heat and it also produces power by sending the hydrogen and carbon monoxide to the engine instead of gasoline. So and it fuels the engine that way. That engine then is a generator, has a generator attached, and produces 20 kilowatts of power. And then all that power can basically go off and run that facility. At the moment, we don't have it hooked up. We're waiting for an electrician. We've gotten approval to do that, but we need the electrician to come in from Clemson, put that together, and then we can power both the composter that's there to deal with compost waste, and also the pelletizer that would pelletize the wood and algae. So I'm going to talk a little bit more about that later. We're using algae as binders, and this comes from our research on fuel. So after we grow the algae, there's leftover, there's waste from that. So that can either be used, could be a food source possibly, or because chlorella is the algae that we're working with, it could actually be, could be a food source as well. But the low value products could easily be used as binders to put into the wood pellets and then increase its BTU value. So that's a current research project that I have as well, that David Thornton is helping me with. Finally, supercritical fluid extraction. This is based again on my work at the dissertation level, and I have 2 of these units in my lab, and we've published a number of publications on extracting this from both fungi and from algae oils. And the main purpose that got me into this was to use carbon dioxide rather than the very toxic, flammable substances that are typically used. Like methylene chloride is an example. The Procter & Gamble still uses methylene chloride for extraction of edible oils. They have a state-of-the-art facility, so they're able to remove most of that methylene chloride, but there's always a little bit left, and it all depends on the FDA or EPA, whatever their levels they allow. They usually have that in there. And of course, over years, FDA gets more strict, so they have to drop the level even more. So they have to come up, with more technology to remove these toxic substances. I'm just thinking, why use a toxic substance at all? You can use natural CO2, and the CO2 basically comes from a sustainable process. It will come from food or fermentation, like a brewery. So CO2 that comes out of a brewery is perfect for the CO2 that we can use for extracting foods and other many other types of uses. So that's kind of wraps up a lot of my research area there. And this is the sustainable pilot plant that we built, this is David Thornton, that helps teach the creative inquiry, and they actually are producing biodiesel as we speak. They're taking all the waste oils on campus. About 3,000 gallons per year is produced between the campus cafeterias, the football games. The 7 games that we have here produce about 1,000 of the total. There's actually about 5,000 gallons that we produce a year, but we convert about 3,000 over to biodiesel. And then part of that will go back into a generator that runs this whole thing. We have a diesel generator on this on the pilot plant. About 5% goes to run the power of the plant, and then the other 95% ends up in the diesel fuel that's running the vehicles on campus, including the new bus. We actually fueled that a couple of times with our biodiesel from the Clemson Transit group. Not the CAT bus system, but the buses on campus. So we've had usually about 7 to 10 students involved in this, and we've had over 200 students participated. Out of that, about 10 of those students have already moved on to the biofuel industry. So we've had a number that have gotten jobs in the biofuel industry directly from this creative inquiry. So it's been a very productive group. And these are some of the grants. This is a recent grant that's submitted to Department of Energy, a really large grant, about $6 million. And this is we're trying to create a whole biorefinery here at Clemson University. And if I get funding for this, then we'll be well on our way. We're already on our way anyway. We already have pilot scale type of equipment, but we want to kind of expand on that even more. And I'm still waiting for word back from DOE about this. This was from our prior Department of Energy grant, and this is what we developed as a biorefinery for ethanol production. And this would come from primarily from switchgrass, loblolly pine, and sweet sorghum, because all 3 of those crops grow very well in South Carolina climate. The toughest of all of that was the loblolly pine. We had to literally come up with a whole new method of pretreatment, which is sort of the beginning. There's a lot of chemical stuff that has to take place to break to open up the cellulose structure of the plant, and then remove terpenes and all kinds of things you would find in pine. And then ultimately get that to where the enzymes the cellulases can go in and break open that sugar structure to break it down to simple sugars. And then once you get into the sugars, feed it to yeast, and the yeast can produce ethanol very quickly just using standard fermentation like at a brewery. So we had to come up with all of this process to do that. And out of that, we actually ended up getting a patent. So I have a patent in pretreatment from that with Arpin Jain, who was my grad student that worked on that project. So I want to move to some of the reasons why this is so important and why biosystems becomes, I think, a potential solution. And let me just kind of show this, kind of shows the update on where we're at dealing with some recent discoveries out of the NOAA Weather Center.
20 to 30 years ago, the Pacific Ocean was dominated by ice that was many years old. This core of old ice survived all year round. Around this core, a smaller fringe of seasonal ice froze each winter and thawed each summer. Old ice eventually drifted out of the Arctic through the Fram Strait. New batches of old ice were built in the Beaufort Gyre. The gyre was a nursery where young ice grew thicker and stronger as it drifted around for many years. Today, summers in the southern branch of the Beaufort Gyre are often too warm for ice to survive. As a result, the amount of thick, old ice in the Arctic has declined significantly. In its place is young, thin ice that's likely to melt in the summer. The small amount of old, thick ice makes the Arctic vulnerable to extreme ice retreat in very warm summers. It's a situation that keeps Arctic wildlife and the people who live there poised on the edge of dramatic and possibly irreversible change.
So it kind of gives you a little idea. So this is just over 20 years that we see this. This is what it used to look like. This is what it looks like now. And by 2050, they're talking about no ice at all there. That will disrupt that climate more so than maybe has ever been witnessed on this planet. So this is the kind of things that we're seeing right now. Why we're not in emergency action right now, I don't know. I don't know how we've gotten so pacified to not take this more seriously. It's perplexing to me, but I'm going to kind of try to emphasize this as much as I can through this talk. So this goes all the way back to Svante Irenaeus, who's one of my favorite people of all time. He's a thermodynamicist that discovered really the climate change effect of CO2. He's the guy that really came up with the greenhouse gas effect on the planet. Of course, Tyndall goes back about 40 years before that. And of course, Irenaeus learned from Tyndall about this. So his basic experiments were just to put CO2 in a chamber, shine a light on it, watch the temperature go up. So he, just like what would happen in a greenhouse. So he actually put this amazingly in 1896. He published this in the Journal of Science. This is one of the top journals in the world. It's very difficult to publish in that journal. You really got to be a top scientist to even get into this journal at all. So, and it goes back hundreds of years, as we can see. And this was 1896. And he basically showed that carbonic acid, as carbon dioxide goes up in the atmosphere, forms carbonic acid with water in the sky, and then creates the global climate change or global warming effect. So he showed this very amazingly accurate, without any satellite images, with very little temperature data to be able to prove his point. He did it through thermodynamic science. And of course, over the next 100 years, we've been able to prove pretty much his stuff very accurately. He was a little bit off, but it was remarkably close on his predictions of what the temperature, how the temperature would change. So he basically showed that up in the Arctic, we would have 7, 8, 9 degrees Celsius increases in temperature. That's why all the ice is melting there. And a lot of that ice is permanent ice that ultimately feeds into the ocean, and that's going to cause sea level rise. We've already seen 1 foot of sea level rise from that. So let's talk a little bit about that math. Since 1750, which is really kind of the beginning of the Industrial Revolution, we've emitted over 600 gigatons of carbon dioxide equivalents. So this also includes methane, other types of strong, potent greenhouse gases. And just since 2000, we have emitted over 50% of that total. So just in like 16 years, that's how fast we're burning fossil fuels. So in the prior 100, 200 years before that, it took us that long to burn that much CO2 or put that much CO2 in the atmosphere. So that's why we're seeing very dramatic changes taking place in the Arctic right now. That's happened just over the past 20 years. We've literally put up half of the greenhouse gases that quickly. That came to a surprise to me when I first found out this fact, because I've seen this, but the rate of this is really phenomenal. And for each 500 gigaton CO2 equivalent that exists in the remaining sources of coal, oil, and natural gas, there's about 5,000 total gigatons possible, but about 500 gigatons will increase the atmosphere by about 100 part per million, and then it results in about a 1 degree C rise in the average temperature of this total planet. So that's why they call it global warming. It's an average of the whole planet. Not some places actually cool, other places get warmer. If you go to the Arctic, it gets a lot warmer up there. So as we can see this, it also results in about a 1 foot or more sea level rise. So if we keep going on with the math, the current rate emissions are about 35 gigatons CO2 equivalent per year. Although we've seen a little decrease in the U.S. since our economy crashed back in 2008. We actually have a 1% decrease, but China, India, all of these other places are increasing pretty rapidly. It's resulted in more than a 2 part per million rise in atmospheric CO2 level per year. At this rate, we will go past 1,000 gigatons of CO2 will be emitted in 30 years. This will result in at least 2 degrees C and 2 foot sea level rise, which will basically put Miami underwater, and a level that's considered pretty much catastrophic, relating to about 50% species extinction, and also leading to some tipping points that I'll show in a minute with Dr. Hansen's work. And he's another one of the authors that's published most of this in Science as well. The cost, each foot of sea level rise combined with sinking land and flood damage will cost on the order of $1 trillion per year. So where's that money going to come from? It's going to come from us. It's going to come from taxpayers all around the world. So that's, you can look at, this is kind of a new normal. That a lot of people like to use that word. But this was based on a World Bank study. A lot of scientists think that's actually very conservative. We're probably looking at a lot more than $1 trillion per year, especially as we start getting closer and closer to tipping points. Cities most at risk, we see some very poverty-stricken cities. We see Miami. We also, in New York, as number 3. So some of the most populated cities in the world are the ones that are in the most trouble. And we've already seen that with Hurricane Sandy. So one hurricane that almost wiped their whole subway system out just through that one event. And New Orleans, as we all know, is another huge issue. And this list goes on and on of mostly the coastal cities. Agriculture is an extreme risk as well. There's a lot of work recently that's going on at looking at the rapidly changing climate zones. We're already witnessing that here in South Carolina. So we're having to adapt to the new climate, to warmer temperatures. So some people say, well, that's a great thing. You can grow more crops. You've got more CO2, so you can get more crops that way, right? But you can't do that with extinct things. When things go extinct, they don't grow anymore. So they kind of forgot about that one little problem. Because a lot of these plants can't adapt quick enough. They can't. They're used to millions of years of adaptation, not 10 years or 5 years. So it's a rate issue that we're really talking about. Midwest breadbasket, California salad bowl. You know, these are we're already seeing extreme droughts that are occurring, and their water reservoirs are rapidly depleting. When that happens, all of a sudden we run out of wheat, we run out of vegetables, two of the most important things for us, and also major exports that help feed the rest of the world. Food prices are going to go very high, so this is I consider an emergency. So let's look a little bit at the efficiency of foods. As we can see, the different types of foods that have impacts in corn, which in many cases is not very sustainable because of the way it's bred. It's not from its natural form. It's from a highly hybridized form that takes lots and lots of nutrients. We have a lot of artificial fertilizers that are fossil fuel based are in that. That's actually at the low when we talk at the energy required. And as we kind of move up this in this area, we see that we get tremendous amounts of energy required to produce, particularly beef. Beef is really almost impossible to produce and make that an efficient process, particularly the way we produce it today. We're producing it primarily by feeding corn. So we grow most of our corn actually goes to making beef. So you lose a huge amount of energy in that process. If you just ate the corn, there would not be that much energy consumed. But by feeding it to another animal and then eating that animal, you end up losing, as you can see, almost 90% of the energy in that process. These are some other graphs that are shown that show the difference between the amount of, in this case, land use, pasture versus cropland. We have irrigation and rainwater from freshwater consumption. So water is another huge issue that I've already mentioned. And then finally, we can mitigate this or see how this is affected through the amount of greenhouse gases that are ultimately put up in the atmosphere from these agricultural products. Again, beef is just way off the charts in this case on water, energy, and the amount of CO2 that's emitted. And they really look at this. About 20% of all of the greenhouse gases that are put up in the atmosphere today are attributed to beef production.
What is purple?
The purple is the rainwater, and then down here is the irrigation. So this is the amount of rainwater that's used in the agriculture, and then the irrigated, and then, of course, this number keeps going up over the years because if we go into drought, you've got to get your water somewhere. They go to irrigation, then you start depleting your reservoirs. And that's what's happening out in the Midwest as we speak today. We can move this to looking at the amount of CO2 that's emitted per person, and it's kind of interesting and kind of shows the different types from meat lover down to vegan. There's not a huge difference between vegan and vegetarian, but as you keep moving up, and particularly with the beef part of it, it increases that footprint tremendously, almost doubles the amount of equivalent CO2 emitted into the atmosphere. And this breaks it down by the types of foods, as you can see here. So I thought it was an interesting graph. So food, I think, relating to agriculture is very critical, but also looking at engines. So engines run agriculture too. We have to have transport. We've got to harvesting equipment. This huge machines that we're producing to do that. Let's take a look at how the difference in efficiency takes place here. This is again in terms of kilowatt hour to carry one person 100 kilometers through this graph. Gasoline off the charts. I predict that gasoline cars are literally going to go away pretty soon. You're not, unless you can go to like using hydrogen gas and making that effective, which they haven't come up with that solution yet. And the hydrogen fuel cell car as well. There was a lot of research put into this about 10 years ago and under the Bush administration, but really the efficiency is not very good there either. Obviously, so we go down to the electric car like Tesla as an example. We cut this down by a third. Going to mass transit is about the same as electric car. Tesla's actually shown on here. So it gives you the standard electric car versus their new cars, and they are coming up with really fantastic new technology. Yeah.
I was just wondering, for a gasoline car, is it more or less for like the size of the car, like a truck versus a motorcycle?
Oh yeah, absolutely. Yeah. I mean, a truck, you're probably getting 10 to 15 miles a gallon, right? And if you go to a diesel truck, you increase that by a third, so you're getting maybe 20 miles a gallon, 25 miles a gallon. Big SUVs. But then you go to the car I drive, which is a Volkswagen Jetta, and it gets 50 miles a gallon. And they just came out with a new car in Volvo in Sweden that we're not allowed to have here that gets 150 miles a gallon. So it's a hybrid electric diesel car. So and then of course, as you can see, there's a lot of other types of mainly getting into mass transit, like trains are really the best. And then Honda came out with a solar car that won the energy challenge in Australia, where they drive across Australia, and it's pretty fantastic. I think it only goes like 5 miles an hour or 10 miles an hour, but it made it across the continent. So it's a start. It's a good start, but it's tremendously efficient. To talk a little bit about this in bigger terms, there's the authors of The Limits of Growth. This is their first book. It looks like an old book right there. But it was very controversial when it came out in the 70s, and everybody thought it was ridiculous. It was the researchers from MIT, so it was one of the top engineering universities in the world. So you'd have to at least think they're onto something, maybe, or hopefully they are, if their reputation is as good as they say. A lot of these people actually moved on to Dartmouth College later, and then every 10 years they came out with a new book. And this last one was 2052. This is another book that I'm going to mention in a minute with James Hansen. But they basically came up with fairly simple models, and you can actually run these models on Excel now. Back in those days, they were using the MIT supercomputer, and it took them a day to crunch those numbers. Now, on your laptop, you can run these models and literally in seconds and come up with the results. And the results kind of come out like this. And this is kind of a business as usual. This is if we just continue to not take this very seriously. Then what's going to happen, probably? And they've been producing these graphs for 40 years now. So the first one was very controversial, but by about 2000, after their third book came out, It was, they were right on target with this model. I mean, as far as human growth and population, they were literally on target with that model. So it's the model is simple, but yet it's just a resource depletion model. That's all it is. And it just takes basic resources, and if you abuse them, this is kind of what you end up getting. And this is what we're seeing in terms of all of their parameters. There's food per capita, there's births and deaths, and then you get the population right here. So which is obviously related to births and deaths. So if the births increase over deaths, you end up with a larger population, and that's of course what we're seeing. We've gone literally from 1 billion people up to 7 billion people just in this 1 century. So in 100 years, we have increased our population by 7 times compared to that over the prior 1 million years of our existence as a species. So we take that, and this population gets to about 2050, and this is the reason why he calls it 2052 in that book. He's predicting at that point we're going to see a very fast population decrease. And this, again, is based on resource depletion, scarcity of food, poverty, and pollution. So pollution is a big part of this model. And originally, it wasn't in the first model. They didn't have CO2 as equivalents as a problem, but they put that in to make the model even more accurate. And this is based on their results right here. Yeah.
So why would you expect that births would go up? Just why do you think? Do you think that they be born and die?
Well, yeah, basically what you end up having, I mean, obviously when you start depleting a population, you have more of a need. A lot of this is just based, if you look at any like poverty country, you see an explosion of population, like Nairobi is an example of that. A lot of times it's just for survival. They have, the kids become slaves, really. They become laborers in a way. And it's very common. Part of it's education. I mean, there's all kinds of interesting theories about population that I think are really interesting. Google, if you go into Google Apps or Google, they actually have a population graph, and they show basically how, with education and the economy, and how people usually populations will decrease quite a bit. And it's actually gotten to the point where some of these countries, they want to repopulate, so to grow their economy. The whole point is to grow the economy. But if you keep thinking that way, it's just about economy, then you've got too many people to feed, and this becomes a problem. A lot of the scientists believe that about 9 billion is what's called the carrying capacity of the planet. It ranges from about 9 to 12 billion. We're at about 8 billion now, so we're very close to getting to what they think is the carrying capacity of the planet. So again, very fascinating models. It'll be interesting to watch and see how this goes. They also produce some of these models if we do make some changes. If we make some big changes, we can completely eliminate this issue. So it is possible. It's still within our ability to make those changes. Yeah.
So you were saying like they predicted it before and it kept to the trend, but all the changes in the trend are happening in the future though. So how do they?
Yeah, I mean you're predicting future. You can't really predict the future. Yeah.
When they say like it holds true to their chart so far, like nothing, not a lot changing drastically from 1970 to 2000. So.
From 70 to 2000. Well, I mean there's been huge changes actually, and particularly pollution.
There's huge changes, but the slope of those really hasn't been altered much. So.
Yeah, right. I mean we can continue on because everything's kind of not. We haven't lost too many species yet. There hasn't been huge changes, but what they're basically predicting is that over that there's going to be a point, there's a break point, what they call the carrying capacity of the planet. If you exceed that, most of this stuff's exponential. So we have exponential increases in population. You'll see even faster decreases in population in many cases. You can look at this with bacteria on a petri dish. And, yeah.
There's also tipping points built into that too, right? Where
no, there's no tipping points here in this particular model.
So that's not what's affecting the sharp
changes
around this time?
That would be really hard to predict a tipping point. Okay. Is everybody familiar with what tipping points are? So tipping points, it's one of the big ones that they're really worrying about is the methane burp, I guess you might say. There's tons of methane that's stored up in the tundra. and it's frozen in there, but basically as it warms very quickly up there, suddenly the methane's going to come out very quickly, and they're already seeing this. There's like bombs literally exploding of methane right now as we speak. Methane goes up, it's about 30 to 40 times more potent than carbon dioxide. It becomes a greenhouse gas, it oxidizes up in the atmosphere, and it turns back into CO2. Which is still a greenhouse gas, a major greenhouse gas. So it will stay there for hundreds of years. So that tipping point is a really scary one. So we don't want to go there. I can promise you that. But yeah.
Ancient gas that's been built up?
Yeah.
Stored? Okay.
Yeah, exactly. Yeah, it's basically a fossil fuel. So what are some solutions? I don't want to make this too negative. And this is where my passion in biosystems are here. And I call this resilient. You can call it sustainable too. Resilient, the definition is tending to recover. So, and I look at it as tending to recover from a devastation that we've caused. We caused it through species extinction since the dawn of the Industrial Revolution. And there's plenty of articles that show this. We can look at many species that have gone through this, and we can look at basically how fossil fuels, exploitation of natural resources, maltreatment of animals and other species has gotten to really record levels at this point, and I think needs to be changed. So to recover from this, I think is vital, is completely necessary. A biosystems approach is,
Where does maltreatment of animals fit into the scheme?
Well, just recently they have, FDA finally got rid of chimpanzee research, right? So they determined that the chimpanzee research was maltreatment of those chimpanzees. And you can have your...
In the atmosphere, I'm trying to figure out where...
Also industrialization of the animal production, livestock, packing animals into tight confinement, etc.
Yeah, this is basically looking more at the social aspects. If you think about sustainability, you can't neglect the social part of it. You know, we usually consider environment and the economy as the main thing. Like, what can we do best for the environment and also keep our economy rolling very well? But you've got to also look at social concerns, and there's a lot of people that are very concerned about this. You may not be, others may not, but they've gotten to the point where they're actually changing behavior because of this issue. Because a lot of people do take that seriously. But how do we address it? I mean, a biosystems approach is the way I look at this is that we work with nature rather than against it. I think we spent the last 100 years trying to defeat nature, and then nature always ends up coming back and winning. I mean, it always happens. You can think about the Monsanto crops. The whole point is to genetically modify a crop that can handle their chemicals, and then ultimately what do you end up creating out of that? A superweed, right? So now we got to have to deal with superweeds in the future. So, I mean, ultimately nature is going to figure out a way to get around this unless we completely destroy it, which is possible. I think it's unlikely at this point that we'll get to that point, but it is possible. But why work against it? Why not work with it? I think engineering in my discipline has been one of the worst at this. We have engineered systems that seem great at the time, but they turn out that the waste products and everything else that's come out of that is very detrimental. And it hasn't been really caught up in the actual cost, what are called externalities. We've neglected that. So we've neglected the idea that CO2 is a pollutant. But finally, the Supreme Court did state that it is a pollutant, and they are starting to act on that. But it took us a long time to figure that out. So again, that is one of the big externality problems, and it's because we really haven't taken a biosystems approach. One of the quotes: "Modern agriculture is the use of land to convert petroleum into food." That's kind of what we have done over the past 100 years, and we've made a lot of food. We feed the world to some extent by doing this. But the problem is we're not looking at the whole picture. We're not considering these externalities. They're going to come back and bite us if we don't do something. Instead, I think we should use natural systems approach to deal with these in cycles, carbon, nitrogen, phosphorus, sulfur, all of the things that make up life. We need to keep that going in a cycle. You don't want to disrupt that. The same thing with global climate change. You don't want to get out of equilibrium with the sun. Like we're building up greenhouse gases, so we're building up heat. That is unnatural. That is something that is not going to do us well in the future. So again, these type of approaches of working with the cycles and living cycles rather than against are important. So the only way to do this is to go to 100% renewable energy. Solution is already here. Sustainable agriculture techniques from moving away from fossil fuel-based monoculture towards permaculture is taking place right here with Jeff's work and the student organic farm as an example, as an excellent example. Sepp Holzer's that I'm going to show you in a second. He's been doing this for years, and they're finally paying attention to some of these new techniques that I think need to be, we need to start moving in that direction. A very rapid transition to renewable energy really needs to take place here. It's already become cost effective, and I'll show you how that's true. It's particularly in South Carolina, you can buy solar now. Solar is actually it's cost effective. When I was putting solar panels at my house, it cost 3 times as much as it does, and that was just from 8 years ago. So it's literally dropped by 2/3 just in 8 years. So the technology is here. We just have to find a way to implement this. We also have to find a way to make agriculture sustainable. We need to have more local production, and you see this is a big movement happening as well. So you're not having to transport food thousands and thousands of miles away. You grow it yourself. And you basically are looking at the true cost. So life cycles, these are all the cycles. If we look at this, water, vapor, there's a major greenhouse gas, but the thing is it has a very short atmospheric life. It only sits there as a cloud, condenses, comes down as rain. But things like carbon dioxide, we're talking hundreds of years of atmospheric life. Methane is about a 12-year life, but then it converts to CO2, so it's still up there in the form of carbon dioxide after it oxidizes. And the one that's kind of neglected a little bit is the nitrogen one. Although, interestingly, the car that I drive, the Volkswagen Jetta, Volkswagen was sued over this very issue. They lost the case, and they've just announced their solution. But it's a $20 billion solution. And apparently, the state of South Carolina is going to get something like $10 million from Volkswagen to address nitrogen issues, nitrogen emission issues. All of their cars are now going to have to put it on the Blue Tech device, which was invented by Mercedes. So the Mercedes cars actually reduce their nitrogen emissions tremendously. Yeah, these are the diesel cars. Yeah, these are just the diesel cars that got in trouble there. And it's basically just through a lie. So some of you all may actually have a car that are dealing with this right now. But
about what their emissions were.
Yeah. They're basically saying that the smaller engine that was really efficient, I mean, it gets 50 miles a gallon, and it's a small engine, was able to not produce up to the EPA limit of what the nitrogen oxides were that were coming out of it. But their bigger cars, they had to put the Blue Tech device in, so that ultimately, it's basically just spraying ammonia into in a catalytic converter, and it will convert nitrous oxide over to nitrogen. So it just goes back to air, basically. So, and it does it pretty efficiently, actually. So it always concerned me when I bought that car that I thought it was odd that I wasn't having to put the ammonia. There's a little reservoir for ammonia to put in there, like in the Mercedes or in the bigger Volkswagens and all these other cars. But they're putting it on now, though. So, and my guess is there's going to be a whole bunch of these available pretty soon because a lot of people are trading them back in, and I could flood the market. Now let me move on a little bit here. I wanted to show this as a permaculture solution, and this I got from Kelly. Just a quick snip from this movie I thought was intriguing.
Let nature work for you. Observe it. Talk to the plants. They tell you if they feel well, if they're doing okay. If you feel with them and put yourself in their place, then things grow everywhere. And then there are no favorable or unfavorable spots. Only more or less capable people who live in cooperation with nature and not in confrontation. If you look over there, you can see the obstruction they are building for avalanches and torrents. They are cementing the whole gutter. That is cultivated monoculture from below to above. The wind tore down thousands of meters there. You can see the rootstock still lying over there, and the snow crushed the rest. And what did they do? Reforested another pine monoculture. And leaning to the left of where the crane is standing, they are now building some concrete barriers. You can only see a part of them. The project costs about $1 million, just so a few houses can be protected. But if you have farmed incorrectly for 30 to 40 years, you cannot change again in a couple of years, go back to natural methods. The people's money is being turned into concrete there.
So this is from a movie that's all about this guy. They didn't really know much about him, and he finally kind of opened up, and now you can go tour his facility, and it's really fantastic. So if you get a chance to watch that movie, I highly recommend it. And how am I doing on time?
It was about 5 minutes.
5 minutes, okay. Let me kind of skip through some of these. So this is actually pulled from Clemson University, and these are some biofungicides that are used for organic agriculture. So you can still look into pest management. And of course, Jeff is an expert in that area, but I thought it was kind of fascinating biological approach. And then I'd like to just sort of emphasize about the energy revolution. This is something that absolutely needs to take place, because we see here still petroleum, coal, natural gas are our main fossil fuel sources, but renewable energy is growing in the United States, and it's growing very rapidly in some other parts of the world. So we've just surpassed the 10% mark recently. This is sort of a consumption of renewables by that gets more detail in that little bitty part of the chart, and then how much non-renewable energy. If we look at our rates, our current rates of production through petroleum, natural gas, coal, and nuclear, about 30 years left of petroleum, 50 years of natural gas, a whole bunch of years left of coal. There's a lot of coal, but luckily we're moving away from that because that's the dirtiest of all of those. It emits 2.2 pounds per kilowatt hour of CO2 equivalent. And then finally, nuclear with existing technology is about 75 years, somewhat cleaner, but then you have to deal with all the nuclear waste and the wars. I'm not so sure that's the best way to go either. And this is the cost of renewables. And this is basically showing recently how the cost of a lot of these new technologies like geothermal, solar, are becoming much more practical. So it's basically the solution, I think, is here based on this study. We can look at this revolution that about 2 to 5 trillion invested could replace most of our power plants, about 5,000 existing. And then Germany and Iowa have already done this. They're moving away and moving into renewables. They're going to surpass their goal of 35%. Iowa's already surpassed 40% renewables. So they're sort of the renewable energy mecca in the United States right now. So other solutions, 100% replacement of fossil fuels. This is kind of a simple 25% strategy. And I get this from solar because solar is available 25% of the time, all the time, so you don't have to really worry too much about the storage aspect, but you do. I mean, storage is one of the major issues with both solar and wind. So they're probably going to be limited at about 25%. Biomass, which is still the #1 source of renewable energy in the world, that could make up the additional 25%, and this also includes the biodiesel that I'm working on right now, particularly to drive larger engines. I think that's going to be around for the next 100 years or so. And then finally, efficiency. So we have become more efficient with our engineering, but there's still a lot further to go, and I think in that area.
Not a single percentage point.
Nuclear they're closing a lot of plants down, but if they come out with some better technologies, and there's some better technologies out there, if that continues, then yeah, I can actually, infusion is another area that is of big interest. The only problem is it always creates a waste, and the waste is very potent, it's very powerful. And it's the same thing with fusion. It's in those reactions, it actually makes the whole reactor turn to radioactive.
Fusion exists?
There was a paper that I think got disproved, really. So it does definitely exist.
The heavy water stuff?
Yeah, I mean, it exists in the sun. I mean, the sun, that's what it does. It's a fusion reactor, but we're trying to mimic what the sun does, basically. Yeah, certainly there's that possibility is still out there. I just don't see it right now. I don't see, it's very expensive. I think that's the big reason. It literally is costing $20 billion for new nuclear power plants. It's gotten skyrocketed out of control on how expensive it is to build these plants. Once they're in place, then they're not too hard.
The other technology pricings are coming down. I would imagine nuclear. I believe I read we haven't built one in 30 years.
Well, yeah, we just built one here in South Carolina. We're the first place in Georgia and Savannah and in Georgia. The first 2 reactors in the United States in 30 years. So what?
Everyone's scared of nuclear though because of like things we passed, and no one wants to actually hold on to nuclear waste. There's like only 2 states that have a facility to hold all the nuclear
right, and South Carolina, one of them.
Because everyone doesn't want it near where they live. So they try not to let that go.
Yeah, exactly, yeah. Okay, other strategies, carbon tax, divestment. Hansen likes the carbon tax green check. It's like one of the most conservative ways to do this. Bob Inglis, who was one of our House of Representatives, he talks about a carbon tax swap. So we would basically increase your carbon tax, and then you'd ultimately swap that with income tax or other, yeah. And then finally, divestment from fossil fuels, and then Kelly states, vote with your dollar, which I think is probably one of the best things that you can do. Do sustainable purchases, investment. All of this is changing. We've already seen a $3.4 trillion divestment just since up till 2016. And this is Bob Inglis now in his new Republican.org, and he's basically trying to convince people that this is a very big deal, particularly on the more conservative side. And then if I can, I guess I don't have time, but I was going to show just the last part of the James Hansen. Is that?
Anyone who needs to leave can go ahead, but if people want to stay and watch the video, yes, that's fine too.
Okay. Yeah, let's do it that way. Is there any other final questions that you have? Okay. Yeah.
What makes it more reprehensible?
This is kind of not, I don't know, it may not be loud enough.
The monarch.
So you think
Oh, yeah. Yeah.
I learned so much today.
Oh, thank you.
I really like to see you on. Pick your brain up.
Oh, yeah. All right. Yeah.
well, I mean, so, the politics gets into this, the economy and jobs.
Oh, yeah. Yeah.
So do you think that, with the new energy focus, stuff that you're talking about, we could move in that direction, but there would need to be government stimulus? I mean, this is not going to happen.
Like grassroots.
Yeah, I mean, it's just not going to happen from the economy just working
Yeah.
naturally. I mean, there's going to have to be some government.
Well, that's the reason why they're pushing so hard on this carbon tax. Because if they get that in, if they can pass that, the economy kind of takes care of itself. It doesn't require a lot of political activity. It's just particularly through those 2 plans, and they're easy to implement, and they actually came close to doing it. In 2010, we were literally 2 votes away from getting a carbon-type tax plan in place. Although it wasn't the best plan. It was a carbon cap and trade thing, which is not the best way to do it, I don't think. But I think if they can make it simple.
That would jumpstart the...
Oh, yeah. Oh, it'd be huge. Yeah. Because you're taxing fossil fuels at the source. That's how it works. It goes straight to the source, and basically what they're going to do is increase their prices, right? So then energy prices go up. So people are going to say, well, screw that, I'm not going to go with that anymore. I'm going with the renewable thing. And it just kind of over time, they do it slowly. and then over about 20 years, they completely transform everything to renewable energy. There's a lot of economic models that show that works. Really, both the carbon tax and green check idea, where they just tax, and then all that money goes back to the people. That's Hansen, and he'll explain it. Let me just show this real quick, and it'll give you a little better idea.
Out of the 20 to 50% of all species that the intergovernmental.
See what happened to the.
What may be more reprehensible if climate continues is extermination of species. Wildlife could be one of the 20 to 50% of all species that the Intergovernmental Panel on Climate Change estimates will be ticketed for extinction by the end of the century if we stay on business as usual fossil fuel use. Global warming is already affecting people. Texas, Oklahoma, Mexico heat wave, and Blaster, Moscow the year before, and Europe.
Oh, yeah, that's what it is.
Were all exceptional events, more than standard deviations outside the norm. Such anomalies covered only 2 to 0.3% of the land area. In recent years, because of global warming, they now cover about 10%, an increase by a factor of 25 to 50. So we can say with a high degree of confidence that the severe Texas and Moscow heat waves were not natural, they were caused by global warming. An important impact, if global warming continues, will be on the breadbasket of our nation and the world, the Midwest and Great Plains, which are expected to become prone to extreme droughts, worse than the Dust Bowl, within just a few decades, if we let global warming continue. How did I get dragged deeper and deeper into an attempt to communicate, giving talks in 10 countries, getting arrested, burning up the vacation time that I had accumulated over 30 years? More grandchildren helped me along. Jake is a super positive, enthusiastic boy. Here at age 2.5 years, he thinks he can protect his 2.5-day-old little sister. It would be immoral to leave these young people with the climate system spiraling out of control. Now, the tragedy about climate change is that we can solve it with a simple, honest approach of a gradually rising carbon fee collected from fossil fuel companies and distributed 100% electronically every month to all legal residents on a per capita basis, with the government not keeping one dime. Most people would get more in the monthly dividend than they pay in increased prices. This fee and dividend would stimulate the economy and innovations, creating millions of jobs. It is the principal requirement for moving us rapidly to a clean energy future. Several top economists are co-authors on this proposition. Jim DePeso of Republicans for Environmental Protection describes it thusly: transparent, market-based, does not enlarge government, leaves energy decisions to individual choices, sounds like a conservative climate plan. But instead of placing a rising fee on carbon emissions to make fossil fuels pay their true cost to society, our governments are forcing the public to subsidize fossil fuels by $400 to $500 billion per year worldwide, thus encouraging extraction of every fossil fuel: mountaintop removal, longwall mining, fracking, tar sands, tar shale, deep ocean, Arctic drilling. This path, if continued, guarantees that we will pass tipping points leading to ice sheet disintegration that will accelerate out of control of future generations. A large fraction of species will be committed to extinction, and increasing intensity of droughts and floods will severely impact breadbaskets of the world, causing massive famines and economic decline. Imagine a giant asteroid on a direct collision course with Earth. That is the equivalent of what we face now. Yet we dither, taking no action to divert
the asteroid, even though the longer we wait, the more difficult and expensive it becomes. If we'd started in 2005, it would have required emission reductions of 3% per year to restore planetary energy balance and stabilize climate this century. If we start next year, it is 6% per year. If we wait 10 years, it is 15% per year. Extremely difficult and expensive, perhaps impossible. But we aren't even starting. So now you know what I know that is moving me to sound this alarm. Clearly, I haven't got this message across. The science is clear. I need your help to communicate the gravity and the urgency of this situation and its solutions more effectively. We owe it to our children and grandchildren. Thank you.
So you can watch this whole thing on TED Talk. It's a 20-minute talk. So, but this is a leading scientist in the world on global climate change right there. So he just retired from NASA just recently. So
he alluded to, irrefutable evidence data showing that, man-made, action is causing climate change. But a lot of people don't buy into that, and it seems like the data might be either confusing or hard to understand, or, why cannot that data be made more clear to people?
He talks about that in the earlier part of the video, because he's sort of one of these nerdy scientists that didn't want to deal with this. And the grandchildren are what kind of got him to start doing this. So he started communicating more with the public.
Well, even when you scientists, even climate scientists talk about it, they say, well, a lot of this would happen anyway, right, without human intervention.
Very few. I think maybe I can only think of like a handful of scientists that are saying stuff like that. Richard Lindzen out of MIT is probably the most, because he's from MIT. All the rest of the scientists up at MIT are on the opposite side of what he's saying. But I would say, it's gotten to the point of like 99% of the scientists are not refuting it anymore. Yeah.
But they're not, I'm not seeing, and maybe it's just, I'm not seeing it, but I'm not seeing, this irrefutable evidence that absolutely, and I totally agree with what he's saying, what you're saying. I'm just saying there's still a question about in people's minds, I think. And that may be why, everyone is so slow to kind of, pick up on this. Yeah,
what's interesting is when he first announced this to the Congress back in 1988, they kind of took it seriously. They're like, this guy knows what he's talking about. And by 1990 or so, George Bush, the president at the time, was actually doing stuff about it, like really taking it seriously. And then suddenly, about 90, 91, the fossil fuel industry said, we could get in trouble here. And they came out with a big campaign to make everything look disputable. And at that time, with the first data, it was about like 70% sure, uncertain. There's 30% uncertainty. By about 2000, it had gone up to 95%. And when you look at all the data and the reports, now it's like very well confirmed. Over the next 15 years of data, they now have satellites that are proving all of these concepts. Back then, they didn't have a satellite. So, and he at NASA was always trying to get the money to get the satellites up there. They finally did. Now they have the evidence is so unbelievable that it's down to like about 1% uncertainty. So there's 99% certainty and 1%. And you can always jump on that 1%. There is a very small chance that all this is made up in nonsense. But I'm not jumping on that boat. I'm going with 99% because that's the clear message. That's what science is all about. All science has uncertainty. It's always going to have uncertainty. And of course, ExxonMobil is a great example of a group that have played on that uncertainty. And they got caught for it. A lot of their scientists actually came up with the same conclusions. A lot of them left the company because of that. But they immediately turned it political, and they've done an excellent job at making this confusing. I don't think it's confusing at all as far as the science goes. What's the toughest part is the solution. What do we do to get to a solution? Political, environmental, everything, all of this.
We're so far away from even, politically, even talking about that. They didn't even really bring it up in the electoral campaigns.
Yeah. Yeah.
You know,
Well, the United States.
in the United
Look at
States,
Canada. Canada was a major issue. It was one of their top 3 issues was climate change in the Canadian election this past that happened last year. All the elections in Europe, in England, the Brexit thing is kind of interesting because England has always been kind of like on the side of like the petroleum industry. The rest of Europe has been very aggressive at trying to address this, particularly Germany. So there's a lot of countries moving fast, and even China, who is the biggest emitter now in the world, they are starting to move aggressively. They are now the #1 producer of solar and wind in the world. So we're falling behind. We have a crazy political system that's so stagnated that even with the U.S. scientists like this, our top U.S. scientists in NASA, informing everybody that this is a problem, are literally ignoring it. It's phenomenal. It's really amazing. The U.S. is the worst, I think, at this so far.
Statistics from the other